In this video, we'll be exploring the product rule and quotient rule for finding differential equations. We will present the theorems and proofs, then demonstrate 3 examples of various types and difficulties.
To begin, we'll show what the product rule theorem is. The product rule is used when your function consists of 2 functions being multiplied. So y equals f of x times g of x. The product rule states that the derivative of 2 functions being multiplied is the derivative of the first function times the second plus the first function times the derivative of the second. Before we start doing examples of the product rule, we are going to actually prove it. So we want you to think of your first function as the mommy function and your second function as the daddy function. And the daddy and the mommy function are going to decide to multiply when we use the product rule. Ha 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 ha. So think of your mommy function as u equals f of x, and think of your daddy function as v equals g of x. Then we can represent the product of u and v as the area of a rectangle, as shown here. So if x changes by an amount delta x, then the corresponding changes in u and v are delta u equals f of x plus f of x minus f of x, and delta v equals g of x plus delta x minus g of x. And the new value of the product of u and delta u and v and delta v can be interpreted as the area of a large rectangle as long as delta u and delta v are positive. So the change in the area of the rectangle is delta u times v equals u plus delta u times v plus delta u minus uv, which can be simplified to u times delta v plus v times delta u plus delta u times delta v, which are represented by the 3 shaded areas of the rectangle. The red area being u times delta v, the green area being delta u times delta v, and the blue area being v times delta u. So to continue with the proof, we divide the entire equation by delta x. Then we take the limit of delta x as delta x approaches 0. Once we simplify that further, we ultimately get that the derivative of 2 multiplying functions is the first function multiplied by the derivative of the second plus the second function multiplied by the derivative of the first. And that's what the product rule states here. So now we're going to do our first example, and we're going to differentiate the function y equals x to the 2/3 times x plus c times e to the x. So we break up our 2 functions that we are multiplying. Our mommy function a is x to the 2/3, and the derivative of our mommy function is 2/3 x to the minus 1/3 using the power rule. Our daddy function b is x plus c times e to the x, and the derivative of our daddy function is 1 plus c e to the x. So now combining those using the product rule, we get y prime equals x to the 2/3 times 1 plus c e to the x plus 2/3 x to the negative 1/3 times x plus c e to the x.
So now let's move on to the quotient rule theorem. When y equals f of x over g of x, then we have our derivative to be y prime equals f prime of x, the derivative of the first function, times g of x, minus f of x times g prime of x, the derivative of the second function, all divided by g of x squared. But before we start using the quotient rule, we're also going to prove it. Unfortunately, our heteronormative mommy and daddy functions have decided to divorce. Aww.
Oh, division, divorce. That's really sad.
Yeah. Anyways, we find a rule differentiating the quotient of the mommy function u equals f of x and the daddy function v equals g of x in a similar way to how we found the product rule. So if x, u, and v change, by amounts delta x, delta u, and delta v, then the corresponding change in the quotient is delta u over v equals u plus delta u over v plus delta v. And subsequently, we finally have v delta u minus u delta v over v times v plus delta v. Next, we take the limit as delta x approaches 0, and we get the limit as x approaches 0 of v delta u over delta x minus u delta v over delta x divided by v times v plus delta v. Further, we continue to take the limit, and finally we have the quotient rule, which states that if f and g are differentiable, then the derivative of f of x over g of x equals the derivative of the first function times the second function, g of x, minus the derivative of the second function times the first function, f of x, all divided by g of x squared. So now let's take a look at another example. If f of x equals x over x squared minus 1, find the derivative. Check to see that the answer to part A is reasonable by comparing the graphs of f and f prime. So first we have our mommy and daddy function again. They're together, but they're still divorced, don't be mistaken. The first function, the mommy function, a equals x, and its derivative is it's 1. And then the second function, x squared minus 1, has a derivative 2x. So when we use the quotient rule, we get f prime of x equals 1 times x squared minus 1 minus 2x times x, all divided by x squared minus 1 squared. You can simplify further, but it's really not necessary. So now let's check our solution by comparing the graphs of f of x and f prime of x. As you can see in the first graph, there is a 0, and in the second graph, there's a horizontal slope in the same spot that the f of x graph crosses the x-axis. So we can see the corresponding horizontal slope in f prime of x is symbolic of the f of x graph crossing the x-axis.
Okay, example 3 is a little different. We're going to use graphs now to find numerical values of derivatives using the product rule and the quotient rule. So, our problem is, if f and g are the functions whose graph are shown, let u of x equal f of x times g of x and v of x equal f of x over g of x. Find u prime of 1 and v prime of 5. So here's our graph of both f and g. What's important in this problem is to remember that when you're thinking of derivatives, you're also thinking of slopes. So when we're finding f prime of x and g prime of x, we're going to use the slopes on this graph, and we can see that they change from positive to negative and from negative to positive in f and g at different points. So let's move on to our solution. First, let's solve for u prime of 1. So we know u of x equals f of x times g of x. Therefore, we know using the product rule that u prime of x is f of x times the derivative of g of x plus the derivative of f of x times g of x. Great. So now we do the same steps we did before. So u prime of 1 is going to equal f of 1 times the derivative of g of 1 plus f prime of 1 times g of 1. So f of 1 is 2. We know that by going to the value of f when x equals 1, and so it's 2. And f prime of 1 is 2 because at the point where x equals 1, the slope of the function f is 2. Rise over run, it goes up 2 and over 1. And now again for g of x, we know g of 1 is 1. We have g here. G of 1 is 1. G prime of 1 is negative 1. Rise over run, it goes down 1 and to the right 1. So we know the slope is negative. And once we plug those values into the product rule, you get u prime of 1 equals 2 times negative 1 plus 2 times 1, which equals 0. So let's move on to v of x. So v of x is using the quotient rule because our functions are being divided, f of x over g of x. So we know using the quotient rule that the derivative of v of x is going to be f prime of x times g of x minus f of x times g prime of x over g of x squared. So we're going to do the exact same thing when finding the values of g of x. So now we plug in 5, v prime of 5 equals f prime of 5 times g of 5 minus f of 5 times g prime of 5 over g prime of 5 squared. So now, f of 5 equals 3. We know that by going to f of 5 and finding that it is equal to 3 here. And f prime of 3 is negative 1/3. We take the slope of the line at f of 5, and we see that it goes over 3 times and down once, so the slope is a negative fraction. And then for g of 5, the value is 2 here, and the derivative of g of 5 is 2/3 by, again, doing rise over run, the run being 3 and the rise being 2, so our slope is 2/3. And now we plug in those values to the derivative that we found here. So we have, just doing out the arithmetic, you get negative 1/6. Negative 6.